review very quickly what we did last time. I'm actually just going to put the formula up here. And then I want to do a little bit of new stuff, and then I've got a handout that covers both those things. So last time we did section 4.3, and this was all about in a situation where you've got two possible outcomes. Which is why it's called binomial. Two possible outcomes. How can I figure out the probability out of some given number that I get so many successes? Right, so that's that. So n is the same as always. It's the number of things I'm looking at. Total, blah, blah, blah. P and Q, what's P?
Probability of success.
Yes, probability of success. And Q would be the probability of
Failure.
that's crazy. So what's P plus Q?
1.
Guys, everybody with me? P and Q, are they opposites of each other?
Yes.
Yes, they are opposites of each other. Therefore, they have to add up to be 1 because they capture every possibility, right? And then you got X, which is the number of successes. Okay. All right, so we will do some problems on this little handout, but the formula for figuring out the probability of X successes is going to be, I've got N things and I want to choose X of them to be successes. So if I'm like 28 people and I want to have 3 of, so 28 choose 3. So then how many P's do I have? How many successes do I have? X. It's a little repetitive. I like that. N of them choose X of them to be successes. So I've got X successes. And the part of the formula that looks the weirdest, but the rest have to be failures, right?
Mm-hmm.
I had N total. I took X of them to be successes. So what's left is N minus X. Okay. That's the formula for that. And then we got the little mean formula for this situation and the little standard deviation formula for this situation. Pop. Yes?
So for that formula, is the n raised to the c power? Is the n raised?
No.
No.
This is N choose X.
Oh, so it's like a
So there's
subscript.
under math probability, there is a NCR, third option. So this means, given N things, how many ways can I choose R of them? You guys all have a calculator, right? So remember that birthday problem we did? Very first day. And we didn't get any pairs. Oh well, a little tear. You just didn't have enough people. But we had roughly, I think the first day we had about 24 people. And let's say I want to choose 2 of them as a pair. Do you see what I'm saying? Because the whole point of that was our brain can't comprehend in a certain group of people how many pairs there are. And that's why the likelihood is higher than we think. So what is 24 choose 2? Can you guys try that out right now? Let's see. I can make sure. Yeah, so make sure you can get 276 for this. That's freaky. If there are 24 people in a room, there are 276 pairs that you can make. Think about that for a second. That is way more than you thought when you first think about that. 24 people in a room, there are 276 pairs, different pairs you can make. That's kind of insane, right? But that just shows you how the brain doesn't latch on to this thing inherently. It doesn't really understand that because it didn't have to. To survive, we didn't have to understand that. So why would we? Now, to pass this class, you got to understand it. So evolve now. All right. Shiesty. Probably not getting all that. I'm way over there. Oh, I did. Sweet. All right. So this is, if I remember correctly, that's all what 4-3 is. Yes. Okay. So I want to talk a little bit about the next chapter. I'm going to get a little bit into chapter 5. Let's see, which order do I want to do this in? Yeah, let's do that first. Anybody play darts ever? Not professionally necessarily. Have you ever thrown some darts in a bar somewhere?
Yeah.
Yes. Have you ever hit somebody in the head with a dart? No. I have. All right. I might have been dart playing while under the influence. DUI. They're fun. So if I have a dartboard, so they look roughly like this, remembering that your teacher sucks at art. Blah, 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 right? Oh, you're right. If I threw several markers at the board, and I only counted the ones that landed in here. Let me see if I can do this real quick. All right. I only counted the ones that landed on the dartboard. Are you guys with me? So if it landed out here, I pretend like it didn't happen. What's the probability I would get in the bullseye? Now, you can't answer that question directly, to be honest, but is it more likely to get in the bullseye than it would be to get into one of these triangles? Why is it more likely to get into this triangle than it is to get into the bullseye?
This is more.
It's bigger. It's got more area. Shouting at you, I'm sorry. I want to make a point of this. We have an inherent understanding of the idea that a visual like that, it's related to the area of it. Sort of like a meteorite coming down is more than likely going to splash in the ocean because most of the earth is covered by water, right? It's going to most likely splash into some water. You guys with me? Very unlikely to go through your car windshield. Let's not think about that next time we're driving. Meteorite, anytime. All right, so if I counted all the ones I hit, there would be very few that go in there, right? Because the area of it's so small. So here's the cool thing. Any visual I create, any graph of a probability situation I create, the probability that it lands somewhere is equal to the area of that place if the whole area is 1. So if I said the area of this dartboard is 100%, which kind of makes sense, the whole dartboard, 100%, right? I could kind of estimate what's the area of this little dude then.
Say 10 or 5?
Sure, I mean, let's 10 or 5%. Let's say 5%, right? So what's the probability that I would get a dart in there? 5% chance. If I'm just throwing darts randomly. Now, if I pick a really good dart player, the probability, if he's aiming for that one or she, then the probability they get it there is higher. So I'm just talking about randomly throwing. Maybe I'm not even looking. I'm just throwing over my shoulder. Somewhere in the world there's somebody that can do that really well, but right, you with me? There's somebody who's never played darts before. I make them throw it over their shoulder and I have everybody clear out. Right? Are you guys semi with me at all? I mean, so this makes intuitive sense to some degree. So here's what's done. Let me give you this. Let's see. Do I want to do it in this order? Yeah. Got a lot of stuff to throw at you. I'm not sure what order to do it in. How long have you been teaching, Jeff? Shut up. Oh, you don't want to work, do you? Little jackass. You have an override. temperature. How can you have a bad temperature? You haven't been on. All right, well, we'll work around it. All right, I'll get over it somehow. I'm going to get over it. First thing I want you to realize, all right, so I have a couple problems at the top. Can you do those real quick? Let's see. Let's do those together. If I flip a coin 14 times, what's n going to be? 14. That's great. So n is 14. Oh, let me take this one. That'll work. What's P and Q? 50-50, right? Looking for heads, so 50% chance of heads, 50% chance of tails. And so part A, how do I put this? Number one, sure, Jeff. Number one says what's the probability I get? Exactly 9 heads. So how would I set that up? What would that formula look like? How many total things do I got? 14. And I want to choose 9 of them to be successes. So how many of these do I have? I'm curious to see if anybody realizes. Anyway, how many successes do I have? 9. So you allow it to be a little repetitive. That's kind of nice. 14 things, choose 9 of them to be successes. So I got 9 successes. How many failures? 5. Somebody might realize whenever it's 50-50, you can just always make that 0.5 to the 14, but it don't matter. Throw that in your calculator to see if we all get the same thing. Let me know if you need some help with your calculator. If you weren't here last time or you forgot. What has happened to you? There we go. This is exciting. Yeah. You can tell I've never sat in these chairs. I had no idea they did that. All right. Reboot is always, hey, all right, let's see. All right, cool. There we go. Nobody got hurt. Yay. Chair almost ate my leg. All right, what do you guys get for that?
0.132.
Yeah, 0.1222. You guys getting that? Is that all right? What happened? Let me do it up here on the overhead. Now that I sacrificed the leg. Projector got it. Oh, thank God. Okay. All right. So, here we go. Maybe. Yay. So if I put this in there, it's going to be 14 math probability choose. 14 choose 9, right? You guys with me so far? Is it pretty cool? I haven't lost anybody yet. Times 0.5 to the 9th. Hit the over button to get back down. Times 0.5 to the 5th. How we doing? Please let me know if you still can't get that. Yes? Say again?
Can you just go through it again?
Yeah, here we go. So 14. Math, probability. Third one is choose. Choose 9. So I got 14 things. I want to choose 9 successes. Do you see how to hit the over arrow to get back up? Very often that's the reason your calculator freaks out. Do you see how it's like, hit the over arrow, please? Okay, you're right. All right, I'll hit the over arrow. Now I'm back up. Times 0.5 to the 9th. I got 9 successes. Hit the over arrow to come back down. So that's the trade-off of the calculator making it look like how we write things is if you're in the exponent, you better come back down. If you're in the subscript, you better come back up. That's the trade-off. Times 0.5, and I want five failures. So I get 14 total. You guys with me? Kabam. Okay, I like it. So how the hell do I do part B, or number 2?
Still.
1 minus that?
No. What's probably at least 1? It's 1 minus what?
0 success.
You can do it, Jeff. It's a technology day. This is awesome. Okay. Yeah, probably at least one head is 1 minus the probability of
0 success.
0. Yeah, that's right. 1 minus probably none. Have we done the probability of none yet? Nope. So what's probably of none? I got 14 things I want to choose. None of them. So how many of these do I have?
0.
None. So how many of these do I have? 14. So be really careful. Don't just do 1 minus whatever the hell probability you've done. Right? It's got to be the opposite of what the question wants for you to use that 1 minus thing. You guys should get something very tiny. So you guys remember how to interpret this. What are you guys getting? Anybody know?
6.
Yeah, so
One.
you get 6.1 blah 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 e
Times
negative
10.
5.
Times 10 to the negative.
Yeah, which means what? Point, how many zeros? 4. 1, 2, 3, 4, 6, there we go. Isn't that yummy? And which you get 0.99994. So if you flip a coin 14 times and you don't get a single head, that is desperately unlikely. It's good evidence that that coin has something weird going on. It's not proof though, because there's a greater than 0 chance that could happen. You guys see that? Maybe? No? Not at all. Check. So the little e dude, we talked about this last time, means times 10 to the. Move the decimal back 5 places, which means once around the whole number and then 4 zeros. Good old scientific notation. All right. Just to continue on this little binomial review, gets interesting. Now watch this. What's the mean? This is a beautiful formula. It's the best formula yet. So if I flip a coin 14 times, you should know without doing any work, really, how many heads you expect. Flip a coin 14 times, you expect 7. Right, which is what you get when you do 14. And then what's the standard deviation? This is the one that we've never been able to do in school. Square root of 14 times 0.5 times 0.5. Biggest mistake I see here is somebody forgets to do the square root. Let me see if this guy is looking at this right. Yep, there you go. Sorry, people. No. All right. How we doing? Anybody got that? Good job. What'd you get?
1.87.
Yeah, 1.87. 1.
0.
Standard deviation at least 3 places. By the way, I told you a while back that you can just make everything 4 places and it covers your ass, because probability has got to be at least 4. So just make everything 4. You're covered. All right. We talked about this last time too. Let me zoom back out a little bit. The minimum expected number of heads, the maximum right? That'll be 2 steps up and down. So if I do 7 minus 2 of these, where do I end up?
3.258.
3.258?
258.
And then if I do 7 plus 2 times that, I end up at,
10.741.
do it again, sir.
10.741.
10.741? So if I go up and down 2 steps from the mean, for normal distribution that catches 95% of the data, I don't know if you guys remember that, but that's why we choose that to be anything outside of there is unusual, because anything outside of there only has a 5% chance of happening. So that is kind of like the most generally accepted rule for unusual is a less than 5% chance of happening. That will change depending on the situation. But that's kind of like with absence anything else, that's what we consider unusual. How you guys doing? Does that make sense? Something has a 5% chance of happening, you're like, well, that would be unusual if I saw that shit. Yes, it would be unusual.
I think the last one, the last number is 2, no?
Okay. Let's see. 7 plus 2 times 1.871. It's got to be, doesn't it? Yeah. Okay, makes sense. All right. So if I flip the coin 14 times and I got 11 heads, would that be freaky?
Yeah.
Yes, officially it would be freaky. There's an official definition of freaky. Anything outside of 2 steps. I like it. Now notice in the middle what I've done. What is this table all about? What was the probability we just got for 9 heads? That first problem.
Yeah.
Yeah, right?
So it's the probability.
Yeah, but this crazy, I just did a quick copy of something that I didn't really do it myself. I should have. They only went 3 decimal places. We'll forgive them. What do you think this means?
0 plus.
Well, what did we get? We actually figured it out. What was the probability of 0? It was 0.00006, right? So what do you think 0 plus means? It means it's not 0, but it's really, really small. It's close to 0, right? I like it. 0 plus sounds like a really weird insult to somebody. But that's what it means. It means it's not 0, it's just a little bit above. It's really small. So this is, if I use the formula for each one of these are the numbers I would get. You guys with me? And what I did was, I did this. I took that and I made it into a histogram. Good job, Jeff. And it looks like we will probably would expect, right? I mean, what's the tallest bar? 7. Why does that make sense? That's what I expect to happen is the, right? So the actual highest bar doesn't have to exactly be the mean, but it's got to be really, really close. And most of the time it will equal the mean. Okay, maybe. Does this picture look normal?
Yeah.
Definitely, right? You guys with me? Why does it look normal? Because it starts low, goes high, and comes back low, and it looks symmetric, all this kind of stuff, right? So watch this. This is kind of cool. No. First thing I want to say is the probability right here, say, well, look, for example, what's probably exactly 6 heads? 183, right? What's the area of this rectangle? What's the width of this rectangle?
1.
1. And what's the height?
0.18. Oh, wait. No. Yeah.
0.183. So what's the area? 1 times 0.183. So this is what I was saying earlier. If I have a visual of the probability distribution, do I? Yep. And I make the whole area of it 1. Is it? Yep. Right? If I add them all up, I get 1. Then any probability question will be equal to the area of that on the picture. That's huge. You guys with me? That's kind of big what we just discovered. If I have a distribution and I can draw it, Any question about probability is just equal to the area related to that.
It's like the integral.
Huh?
It's like an interval, but different.
Yes, dude, we're going to do exactly intervals here in a bit. All right, this I'm going to come back to later. All right, so what if I had don't lose this handout, by the way. We're going to bring it back later. So we're going to do this part later. You can do it right now, it doesn't matter. The probability is connected to the area that we are interested in. So if I had a distribution that was just straight across like that, this would be called a uniform distribution. When I say the word uniform, what do you guys think?
It's like the same.
Uniform. If I say uniform, what do you see in your head? Uniform.
All the same.
Yeah, you see somebody in a uniform, don't you? Most of the time you would. I don't know, maybe you don't. I'd be really curious if you don't. But uniform means they're all the same. So if I have a uniform probability distribution, that means every piece has the same probability. If I roll a normal die, is there more likely or less likely to get a certain side? They all have the same probability, don't they? So that would be a uniform probability.
Yeah.
So this would kick so much ass if somebody asked me the probability from here to here, because then I just have to figure out the area of it. That would be it. And that's a big frickin' rectangle. Yes. Maybe. All right. So my whole point with this right now is to connect the area to the probability. As long as I draw it and I make the whole area 1, the probability of anything, a piece of it, will equal the area of that piece. Now look at this. What is this curve? This is the what curve? Bell curve. Normal curve. There it is. I like it. If I wanted to know the area of a piece of this, now I put the numbers in there. We're going to figure it out later ourselves. If I want to know the area of this piece, is that an area you've ever done in geometry?
No.
Almost a trapezoid, but one side of it melted. Have you done melted trapezoid areas? No. I like it. So later, when we get to chapter 6, we're going to need some help. Rectangles, I'm all over it. Triangles, I gotcha. Trapezoids, all right, what the hell is a formula, but then I could do it, right? But once I got a side that's curvy, I'm screwed. So we're going to have some help in chapter 6, but for chapter 5, it's going to be a bunch of frickin' rectangles. So let's try a problem now. Let's see. Did I bring... Sure, Jim. Yeah. No. It's got shit on it. All right. Not actual shit. It's got stuff. So if I had, for example, if I had a uniform distribution. So let's say it takes anywhere between 10 and 15. So let's say somebody's going to be at my house, and it could be, if there's no traffic, it takes them 10 minutes. If there's a lot of traffic, it takes them 15 minutes. You with me? And it's not more or less likely. I have no idea what it's going to be like necessarily. So it's evenly distributed between 10 and 15 as to how long it's going to take them to get to my house. So that's the picture of it so far. Is the area, how can I make the area of that? What's it got to be? The whole area has to be, you can do it. So I said earlier, if I can graph the situation and the whole area is 1, because that's related to all the probabilities adding up to be 1, then any question about what's probably, it would take me more than 11 minutes, whatever, it's just going to be equal to the area I see. Can somebody tell me how tall this bad boy has to be so the area is 1? What's the width? 5.
So 1.
So what's the height got to be to make the area 1? So let's reword that. What number multiplied by 5 gives you 1?
No.
Oh, no.
1/5.
1/5. The reciprocal, right?
Yeah.
What do reciprocals do? They make something become 1 when you multiply. What's 5 times 1/5? 1. So if I would have given you different numbers down here, can you find the height?
Yeah.
So this height is 1/5. Why is the height 1/5? Because that's what makes the whole thing 1. Really? Does that make sense? If the probability that the person, my friend, is going to get to my house is evenly distributed from 10 to 15 minutes, they never get there less than 10 minutes, they never get there more than 15 minutes. I know this isn't exactly realistic and I don't apparently give a shit, but it can be close enough to that. Are you guys with me? And it's uniformly, I have no idea, 10 to 15, somewhere in there, right? Then the total probability between 10 and 15 should be 1. And what we just said earlier is the area is related to the probability. They are the same if I make the area of that whole thing 1. That's the equivalent to all the probabilities adding up to be 1. All right, Jeff. So let's do this. So what if it was from, let's do a couple quick fire ones, from 2 to 19. Don't say anything out loud. Take a minute. All right, what would the height be? 1 over 17. Right? The width is 17, so the height must be 1 over 17 to make the whole area 1. Here's a niftier one. What if it was from 1.7 up to 2.4?
Should be 1.42.
And we can be better than what some of you guys are doing. What's the width?
0.7.
0.7. So what's the height? 1 over 0.7. Which is 10 over 7. Which is better than any decimal you want to give me. So how do you always find the height? It's 1 divided by the width. That's how you can guarantee the whole area to be 1. Please let that make sense. We're talking about rectangles. Areas length times width. That kicks so much ass. So the length and width just have to be reciprocals to make the area always come out to be 1. All right, so I'm coming back to my main problem. What is the probability that my friend gets there somewhere between 12 and 14 minutes after they leave their house? Can you draw that in the distribution? Try to put that situation in there. So watch, let this be. 12 is somewhere right here, right? 14 is right there maybe. So the